Let's suppose we have a complex number which is given by z equals to a plus ib. What we'll do, we'll try to express this given complex number in its polar form. So z can be also represented as r multiplied to cosine of theta plus iota times sine theta. Here we have used the fact that r can be represented as square root of a squared plus b squared, where a and b represents the real and imaginary part of the complex number, and theta, that's simply the argument of our complex number, and this is defined as the inverse tangent of the imaginary part, which is b divided by the real part, that's a. Now we also know that a cosine and sine are periodic function, meaning cosine theta can be also represented as cosine of 2 pi m plus theta, and sine theta, that's also a periodic function, can be also represented as sine of 2 pi m plus theta. Here m can take the value from 0. M is an integer, it's an integer. It can take the value 0, 1, 2, 3. Right. Now what we'll do, we can rewrite our given complex number in the polar form as z equals to r times, we have cosine of, so instead of theta, we will have 2 pi m plus theta plus iota times sine of 2 pi m plus theta. Now if we take the nth root of the complex number, so nth root will be z raised to the power of 1 over n, then we can represent our polar form as r raised to the power of 1 over n. Then we have cosine of 2 pi m plus theta plus iota times sine 2 pi m plus theta whole raised to the power of 1 over n. Now what we can do, we can use the De Moivre's theorem. So De Moivre's theorem states that whenever we have cosine of theta plus iota times sine theta raised to the power of n, that this becomes equals to cosine of n theta plus iota times sine of n theta. Now in our case, our n is actually 1 over n, which means the nth root of our complex number will then become r raised to the power of 1 over n multiplied to cosine of 2 pi m plus theta over n plus iota times sine of 2 pi m plus theta over n. Here we have applied the De Moivre's theorem. Now, this is what is referred to as the nth root of our complex number z. So if we have to take what does the m value represent here, meaning let's say if we want to take the square root, if we want to consider the square root of our complex number z, then here the m value will be m equals to 0 and m equals to 1. If we want to find out cube root of our complex number z, then m will take the values 0, 1 and 2. Similarly, the fourth root of our complex number z will be for values of m equals to 0, 1, 2 and 3. So that's how we can find out the nth root of any given complex number. Now let's try out this idea with the help of an example. Now let's say we have our complex number which is given by 1 plus square root of negative 3. First of all, we'll rewrite a complex number. We have z given by 1 plus square root of negative 3. But we know that iota squared, that's given by negative 1. So in place of negative 1, we have 3 times iota squared, such that our complex number becomes 1 plus iota times square root of 3. So this is a complex number, and we also want to express it in the polar form, such that our value will be given by square root of the real part, square it, and then add it to the square of the imaginary part. And then we'll take the square root. So this is going to give us a value 2. And the argument of our complex number, argument of z, which is actually theta, that's given by the inverse tangent of the imaginary part, which is square root of 3 divided by the real part. So we have tangent inverse of square root of 3. Now we know that square root of 3, that's actually tangent of pi over 3. The tangent inverse of tangent of pi over 3, that's give us That will give us the value pi over 3. So here we have our argument as pi over 3. That means our complex number z, which is 1 plus iota times square root of 3, that this can be also represented in the polar form as 2 times cosine of theta, which is pi over 3, plus iota times sine of pi over 3. So this is a complex number represented in the polar form. Or we can also represent it as z equals to 2 times. So instead of cosine of pi over 3, we will have 2 pi m plus pi over 3 plus iota times sine of 2 pi m plus pi over 3. So this is the complex number. Now we have to raise it to the power of 3/4. So we have z raised to the power of 3/4. That will be simply equals to 2 raised to the power of 3/4. And then we have cosine of 2 pi m plus pi over 3 plus iota times sine 2 pi m plus pi over 3. And this entire expression is raised to the power of 3 over 4. So let's further reduce this. So we will apply the De Moivre's theorem. Then this should give us cosine of, now 3 over 4 will get multiplied to 2 pi m plus pi over 3 plus iota times sine of 3/4 multiplied to 2 pi m plus pi over 3, which will be equals to 2 raised to the power of 3 over 4. So this is going to give us cosine of, we will multiply 3 over 4 with 2 pi m plus pi over 3. So this is going to give us 3 pi m divided by 2 plus pi over 4 plus iota times sine of, so we have 3 over 4 multiplied to 2 pi over m. So this is also going to give us 3 pi m over 2 plus pi over 4. Right. So this is the value of z raised to the power of 3 over 4. The task next would be to select the values of m, such as this is going to help find the distinct roots of the complex number. So before specifying the values of m, so let's start with z raised to the power of 3 over 4. So this can be also represented as z cubed whole raised to the power of 1/4. Meaning we are actually trying to find out the fourth root of the complex number z cubed. So the fourth root of the complex number simply means that we need to consider the 4 values of m, which will be 0, 1, 2 and 3. So let's begin with our first value. So let's consider m is equals to 0. So this is going to give us one distinct root of our complex number. So that means we will have z raised to the power of 3/4. This will be equals to 2 raised to the power of 3/4 whole multiplied to cosine of pi over 4 plus iota times sine pi over 4. So that means we now have 2 raised to the power of 3 over 4 multiplied to cosine of pi over 4, that's 1 over square root of 2, plus iota times sine pi over 4, that's also 1 over square root of 2. So that means we have 2 raised to the power of 3 over 4 divided by square root of 2, all multiplied to 1 plus iota. Now square root of 2 means, let's do it separately. So we have 2 raised to the power of 4 divided by square root of 2, which is actually 2 raised to the power of half. And we can take it to the numerator. So we have 2 raised to the power of 3/4 minus 1/2. So this is going to give us 2 raised to the power of 1/4. So that means we are getting a value 2 raised to the power of 1/4 multiplied to 1 plus iota. So this is going to be one distinct root of our complex number z, and we are obtaining this value for a particular value of m, which is m equals to 0. Now we will consider the value of m to be equals to 1. So we'll have m value equals to 1 such that z raised to the power of 3/4, this will be equals to 2 raised to the power of 3/4 all multiplied to cosine of 3 pi over 2 plus pi over 4 plus iota times sine of 3 pi over 2 plus pi over 4. This is going to give us the value 2 raised to the power of 3 over 4 multiplied to, now here we have 3 pi over 2 plus pi over 4. So this simply means that we have an odd multiple of pi over 2. Cosine will become sine. And then this will become sine of pi over 4. Now 3 pi over 2 plus pi over 4. That means we have our first, second, third and fourth quadrant. So 3 pi over 2, that means we are in the third quadrant, but we are also adding pi over 4 to it, which takes it to the fourth quadrant. And in the fourth quadrant, now that the cosine function is positive, so that means the value of this particular cosine is going to be positive. Then coming to sine, 3 pi over 2 plus pi over 4. So since this is also an odd multiple of pi over 2, so sine will become, we already have iota, cosine. So we'll have cosine of pi over 4. Now in the fourth quadrant, our sine function is negative, so we'll have negative iota times cosine pi over 4. This is going to give us the value 2 raised to the power of 3 over 4 multiplied to, so we have 1 over square root of 2 minus iota times 1 over square root of 2. And this is also going to give us the value 2 raised to the power of 1 over 4 multiplied to 1 minus iota. Fine. So we have obtained the second distinct root of our complex number z. Now we will consider the third case, which will be for m equals to 2. So we have z raised to the power of 3 over 4. This is going to be equals to 2 raised to the power of 3 over 4 multiplied to cosine of, so here we have 3 pi m. So that means 3 pi multiplied to 2 divided by 2 is going to give us the value 3 pi. So we have 3 pi plus pi over 4 plus iota times sine 3 pi plus pi over 4. So let's obtain this value as well. So we will have 2 raised to the power of 3/4 multiplied. So here we have 3 times pi. So this is just simply an even multiple of pi. So cosine will stay as cosine. So we have cosine of pi over 4. Now 3 pi means what? We are in the, so 3 pi is actually 6 times of pi over 2. So this is an even multiple of pi over 2. So that means we'll be 1, 2, 3, 4, 5, 6. That means we are in the second quadrant whenever we consider 3 pi. Now we are also adding pi over 4 to it, which will take us to our third quadrant. And in our third quadrant, we know only the tangent function is positive. So we will get negative cosine of pi over 4. Similarly, sine 3 pi over 4, this is going to give us iota times sine pi over 4. And in the third quadrant, sine is negative. So we have negative iota sine pi over 4. So this is going to give us 2 raised to the power of 3 over 4. So we'll take out negative as the common factor. We have 1 over square root of 2 plus iota times 1 over square root of 2. Or simply negative 2 raised to the power of 1/4 whole multiplied to 1 plus iota. And finally, we'll consider for m equals to 3. So this is going to give us z raised to the power of 3/4 equals to 2 raised to the power of 3/4. So we have cosine of, so we had 3 pi over 2 plus pi over 4. That was the argument of our cosine function. So if we substitute the value of 3 m with 3, so we will get 9 pi over 2 plus pi over 4 plus iota times sine 9 pi over 2 plus pi over 4. So let's find out these values as well. So we will have 2 raised to the power of 3/4 multiplied to, so 9 pi over 2 means we have an odd multiple of pi over 2. So that means our cosine function is going to become sine. So we'll have sine pi over 4. And similarly, sine 9 pi over 2, this is also an odd multiple of pi over 4, pi over 2. So sine will become cosine pi over 4. And we have iota. Now let's also consider the sine. Now 9 pi over 2 means we are in the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth quadrant. But then again, we also have pi over 4 added to it, which will take it to the second quadrant. And we know that in the second quadrant, only the sine function is positive. So the first one, this is a cosine function. Don't get confused with the value of what we are getting here. We are only talking about the cosine function here. This is going to be negative. And then coming to the imaginary part, so here we have a sine function. So in the second quadrant, the sine function is positive, so we'll get a positive value. So this is going to give us 2 raised to the power of 3/4 multiplied to negative 1 over square root of 2 plus iota times 1 over square root of 2. or simply 2 raised to the power of 1/4 multiplied to -1 plus iota. So we have obtained all the 4 values. So that means the roots of our complex number z raised to the power of 3/4. So those will be 2 raised to the power of 1/4 multiplied to 1 plus iota. That was the first one. Then we had 2 raised to the power of 1/4 multiplied to 1 minus iota when m equals to 1. Then for m equals to 2, we had 2 raised to the power of 1/4. This was -1 minus iota. And for m equals to 3, we obtained the value 2 raised to the power of 1/4 multiplied to -1 plus iota. So let's go to the next example. Let's say we want to obtain the cube root of our imaginary number iota. And that means we want to find out iota and its cube root. So this is what we need to find. So our task will be to convert the complex number to its polar form. So here we have our complex number z, which is simply iota, or we can also represent it as 0 plus iota times 1. So here our real part is simply 0. Then our value, so that will be equals to square root of real part squared plus iota, the imaginary part squared. So we have 0 squared plus 1 squared, which is simply 1. Then the argument of the complex number will be inverse tangent of the real imaginary part divided by the real part. And this is going to give us a value pi over 2. So that means in our polar form, which is given by r of cosine of theta plus iota times sine theta, this will be equals to 1 multiplied to cosine of pi over 2 plus iota times sine of pi over 2. Now we know that our cosine and sine are periodic functions. So that means our complex number z can be also represented as cosine of 2 pi m plus pi over 2 plus iota times sine 2 pi m plus pi over 2. And what do we want to find? We want to find out the cube root. So that means z raised to the power of 1/3. That will be equals to cosine. So we are straight now going ahead and applying the De Moivre's theorem. So we have cosine of 1/3 multiplied to 2 pi m plus pi over 2 plus iota times sine 1 over 3 multiplied to 2 pi m plus pi over 2. That will be equals to cosine of 2 pi m over 3 plus pi over 6 plus iota times sine 2 pi m over 3 plus pi over 6, which will be, so this is the cube root of our complex number iota. This is the general form. Now since we are considering the cube root, so the values of m would be 0, 1 and 2. So these are going to give us the 3 distinct roots of cube roots of iota. So let's begin. So we will first consider let m be equals to 0. For this case, we have z raised to the power of 1/3. This is going to give us 1 of the root of iota, which will be cosine of pi over 6 plus iota times sine of pi over 6. So pi over 6 means we have square root of 3 over 2 plus iota times 1/2. So this is one of the cube root of iota. Then we will consider the next value. We'll consider the m to be equals to 1. For m equals to 1, we have z raised to the power of 1/3 given by cosine of, we'll have 2 pi over 3 plus pi over 6 plus iota times sine 2 pi over 3 plus pi over 6, which is equals to cosine of, so here we'll have 5 pi over 6 plus iota times sine 5 pi over 6. Now 5 pi over 6 means cosine can be also represented as cosine of pi minus pi over 6 plus iota times sine of pi minus pi over 6. Now what is pi? Pi actually means 2 times pi over 2. So we have an even multiple of pi over 2. So whenever we have an even multiple of pi over 2, so cosine remains as cosine, but we'll have cosine of pi over 6. And now we'll have to check in which quadrant pi minus pi over 6 lies. So here we have an even multiple of pi over 2, which means we are on the first second. So we are on the second quadrant where the value is 2 times pi over 2. But we're also subtracting pi over 6 from it. And pi over 6 means it's less than pi over 2. So that means we're still in the second quadrant. And in the second quadrant, only the sine function is positive. Everything else is negative. So we'll have a negative cosine of pi over 6 plus iota times and sine pi minus pi over 6. So that will be positive pi over 6. Which is going to give us, so we have negative square root of 3 over 2 plus iota times half. So this is going to be the other root of a complex number. And then we are going to consider m value equals to 2. So instead we have z raised to the power of 1/3. So this will be equals to cosine of, so remember we had an argument theta given by 2 pi m over 3 plus pi over 6. This is going to give us 4 pi, since we are considering m value to be equals to 2. So we have 4 pi over 3 plus pi over 6 plus iota times sine 4 pi over 3 plus pi over 6, which will be equals to cosine of 9 pi over 6 plus iota times sine of 9 pi over 6. Now cosine of 9 pi over 6, that simply equals to cosine of 3 pi over 2. Or we can have 3 pi over 2, let's take minus 0, plus iota times sine 3 pi over 2. So that's the reduced form of 9 pi over 6. And we'll have minus 0. That will become evident in a moment. So here we have an odd multiple of pi over 2. So whenever we have an odd multiple of pi over 2, then cosine will become sine and the sine will become cosine. We also have an iota here and this will become simply sine 0 and we will have cosine 0. Then the question is, in which quadrant does it lie? So 3 pi over 2 means we have 1 pi over 2, 2 pi over 2, 3 pi over 2. So that means we are in the third quadrant, and in the third quadrant only the tangent function is positive, everything else is negative. So we'll have negative sine 0 and negative iota times cosine 0. So sine 0, that's simply 0, minus iota times cosine of 0, that value is positive 1. So we have negative iota. So this is going to be the third root, distinct root of z raised to the power of 1, or the cube root of a complex number. So we finally obtained all the three roots of our the cube roots of the imaginary number iota. So those came out to be, we had negative iota, this is one of the root. Then we had square root of 3 over 2 plus iota times 1/2. Then we had negative square root of 3 over 2 plus iota times 1/2. So these are the three complex roots of the cube root of our imaginary number iota. Let's do one more problem. So let's say we want to find out the cube root of -1. So we will begin by considering z to be equals to, we have -1. This is going to be a complex number. Our task is to find out cube root of -1. So we'll consider z equals to -1, which can be also represented as -1. So here we only have the real part, the imaginary part is simply 0. So we have iota times. Now our goal is to convert this particular complex number z into its polar form. Now if we consider our Argand diagram, so here we have our x-axis, which represents the real part of a complex number z, and y-axis represents the imaginary part of a complex number z. Now clearly we see that z equals to -1 means we have only a complex number lying on the real axis. So this is the value for our complex number. And what is the argument? So this is going to be our argument theta, which from the diagram is evident that it's going to be equals to pi. So that means we can represent in our polar form as cosine of pi. And we also know that cosine of pi, that value is -1 plus iota times sine pi. So this is a complex number. Now what we can do, we can use the fact that cosine of pi can be also represented as 2 pi m plus pi plus iota times sine 2 pi m plus pi. So when we want to find out the cube root of our complex number z, we can simply apply de Moivre's theorem to get 2 pi m plus pi divided by 3 plus iota times sine of 2 pi m plus pi over 3. So this is the general form of the cube root of -1. Now what we can do, we can find out the roots by considering 3 values of m. We'll first consider m to be equals to 0. When m equals to 0, then cube root of a complex number will be simply equals to, so we will have cosine of pi over 3 plus iota times sine pi over 3. So cosine of pi over 3, so that's half, plus iota times sine pi over 3, so that's square root of 3 over 2. So this is going to be one of the root. Then we will consider the next value of m, which will be equals to 1, and this is going to give us z raised to the power 1/3 equals to cosine of, so we have m equals to 1, so we'll have cosine of, so 2 pi plus pi, that will be 3 pi over 3, we will simply have cosine of pi plus iota times sine of pi. So cosine of pi, that's -1, and iota times sine pi, that's 0. So -1 is going to be the second root of cube root of -1. Now we will consider m value to be equals to 2 to find out the third cube root of -1. So we have z raised to the power of 1/3 equals to cosine of 2 pi times 2, so that's 4 pi. So we have 4 pi plus pi divided by 3 plus iota times sine 4 pi plus pi over 3. So 4 pi plus pi over 3, so that's actually 5 pi over 3. We will have cosine of 5 pi over 3 plus iota times sine 5 pi over 3. We can also represent 5 pi over 3 as 2 pi minus pi over 3. It would mean exactly the same thing, but it will help in finding out the value of each of the cosine and sine. So we have sine 2 pi minus pi over 3. Now we know that 2 pi, so that's also equivalent to 4 multiplied to pi over 2. The reason we're writing in this particular format, so this tells us that 2 pi or 4 times pi over 2, it's an even multiple. So since 4 is an even number, so here we have an even multiple of pi over 2. So whenever we have an even multiple of pi over 2, then cosine will remain as cosine and sine will remain as sine. So we'll have cosine of pi over 3 and iota times sine of pi over 3. Now we'll also have to take care of the sine. So 2 pi means 4 times pi over 2. So if we consider our quadrant, so we have 1 pi over 2, then 2 pi over 2, 3 pi over 2, and 4 pi over 2. So that means we are in our fourth quadrant. Now we are also subtracting negative pi over 3 from 2 pi or 4 pi over 2, but pi over 3, that's less than pi over 2, that means we're still in the fourth quadrant. And we know that in the fourth quadrant only the cosine function is positive, rest is negative. So we have positive cosine pi over 3, but sine 2 pi minus pi over 3, this is going to become negative iota times sine pi over 3. So this is simply per half, positive half, then we have negative iota times square root of 3 over 2. Oh, we have successfully obtained the 3 cube roots of -1. So they are -1 was one of the value, then we had half plus iota times square root of 3 over 2, and the other one is half minus iota times square root of 3 over 2. So this is how, using de Moivre's theorem, we can easily find out the cube root or any roots of any given complex number.